You all met Kishore because he was here this morning. Kishore is a professor in the Hildebrand Department of Petroleum and Geosystems Engineering. And today he's going to talk about increasing ultimate recovery and operational efficiency. So I'll pass it over to you, Kishore.
All right. Do you see my PowerPoint?
I do.
Okay, now I'm going to go to full screen. I hope you see that.
Yes, all good.
Let's see if I can pick up a pen. No, I don't have a pen.
I can see your cursor.
Yeah, I think I'll just go with this cursor.
Yeah.
All right. So let's talk about increased oil recovery. So I have a little, okay, how do I advance that? I guess I have to go here. Okay. All right. So I'll give a little introduction. Then I'll get into overview of EOR, just the big scale picture. Vanessa has already started introducing CO2 EOR. I'll go into the other ones. Then I'll get into a little more details of polymer flood, which are happening in quite a few places, and talk a little bit about gas Huff-n-Puff in shale wells. Okay, then we'll summarize. And if you have any questions, please feel free to ask me in the middle also if you want to. All right, so I just want to give a perspective of global oil resource. So in x-axis over here is how much oil we have produced and may in future produce. And on the y-axis, I have some kind of oil price. That thing, of course, changes with time and all that. But that's a rough indication. So we have produced about 1 billion barrels of oil, 1 trillion barrels of oil in the last 150 years. All right, little over 1 trillion actually. And but OPEC and Middle East have at least another trillion to produce. They know about it. It's a matter of producing it in the future. And if you look at rest of the countries in the world, they probably have another like 0.8 trillion or so available to be produced in future. So these are all conventional oil with conventional techniques. If you go into deep water, there is another like 100 million barrels. 100 billion barrels, because these are all trillions. Okay. Then there is Arctic, of course, there is a potential, but we are not producing it. There is ultra deep ocean oil deposits. And then there is EOR. So I just want to show you where EOR fits in over here. Okay, so EOR has the potential to produce about 500 billion or so amount of oil. Because every barrel of oil we produce here, we probably leave around 2 billion barrels of oil in those reservoirs. Okay, so there is quite a bit of oil there, of which we can produce part of it. That's by EOR. Then there is heavy oil, and lots of it in Canada, Venezuela, etc. Then there is oil shale. This is kerosene. This is not shale oil. Okay, this is kerosene. And we know that in Colorado and Wyoming, we got lots of kerosene. Those are shallow deposits of these oil shales. They can be produced with a thermal technique. And finally, this is shale oil that we are producing right now by taking these tight oil reservoirs and fracturing it and producing. So I just went over the x-axis. Let's look at the y-axis of some of these things. So the traditional oil we produce costs of the order of to produce about $20 a barrel or less. Okay? So this is roughly $20 or so, roughly. If you go into deep water and ultra deep, now the wells are going to cost more. So the oil is going to cost more. So the prices keep up to $40. EOR is producible in the range of $20 to $50. Okay, so we'll talk about different techniques that cost different amount and are applicable to different kinds of oils. So, but the cost is a lot more than the conventional oil. It's of the order of $20 to $50. Heavy oil similarly costs a little more. These kerosenes cost much more, and these oil shales also cost quite a bit, in the range of $30 to $75 in this scale. But good thing about the shale oil is the project time is a lot shorter over here. You can decide, and in 6 months you can be in the field. In a couple of years you can get your money out. That's why this is happening fast. Whereas a lot of these other projects take a lot more time. You know, for deep water, you have to plan for many years. You put all these platforms and other things. So it takes time. So the other techniques take time. So even though they may be a little bit cheaper, people can't commit to it because they take time and they take money. All right. So that's sort of the big picture. So now let's, this is probably, you have seen before. We have, these are different methods of seeing the, recovering the oil. We have the first method we typically apply is primary recovery. So the reservoirs are high pressure. All we do is depressurization. We punch in a few wells and produce stuff that lowers the pressure. Things expand, they come out. But by that technique, we get only like 10 to 20% of the oil that's there comes out that way. Sooner or later, pressure equalizes and we stop producing. All right. So then what we typically do, we do what is called secondary recovery. What really it means is water flood. We inject water into these reservoirs that goes and pressurizes the reservoir and pushes more oil out. Okay. By that, we get another 15 to 20% of the oil out. Okay. So at the end of this, actually, we produce roughly 30 to 40% of the oil. So about 65% of the oil is still there in those reservoirs, and we know of them. Okay. So the enhanced oil recovery or tertiary recovery is aimed at getting part of these oils out. Okay. So there are different techniques. There are thermal techniques. There are solvent techniques like CO2 that you guys discussed in the last lecture. And there are chemical techniques. And we'll talk about these in a little more detail. But before we talk about that, let's think about this, how much oil is left behind. In a standard light oil, good reservoir, unfractured type of reservoir, 50 to 70% of the oil is left behind after depressurization and water flood. And typically oil companies will do these two things and move on. If they find another reservoir where they can do this, which is much cheaper, they would rather do that than do anything else. So 50 to 70% of the oil is left behind. Now, if that light oil reservoir is fractured or highly heterogeneous, this amount of oil that's left behind will be even higher because the production will be low. So 70 to 90% of the oil may be left behind there. If you go to shales, which are very tight reservoirs, where the permeability, the flow capacity is like 10,000, 100,000 times smaller than that of our conventional reservoirs. This amount of oil that we produce is 5 to 10%. So 90 to 95% of the oil is left behind at the end of these. If you go to a viscous oil reservoir, now the oil is very viscous, so it's like a glue almost, or molasses. So it doesn't move very well. So by these techniques, you don't produce much. You have to use some other enhanced technique. So let's ask the question, why is oil left behind? Okay. All right, and where is the oil left behind? So we know that our reservoir is generally pretty complex. There are a lot of heterogeneities in it. There are tight rocks, there are permeable channels, there are faults, there are barriers. Not only that, we can put in wells only at certain places. Okay. So it's not possible to sweep the whole reservoir. And if you really look at these reservoirs at a very small scale, at a micron scale, they look like this. And there are pores which are connected to each other, but there are tight pores, big pores. So very complex structure. So when we do depressurization and then water flood, we take out oil from the highly permeable parts of the reservoirs. Okay, so a part of the reservoir is not swept. Okay, just for imagine from this sketch, you have these wells, and yellow is where your injected fluids or water goes through and pushes out some oil, but water doesn't go through these green areas, so that's left behind. Okay, so only a part of the reservoir is swept, the part is not swept. We call that efficiency sweep efficiency, and this is of the order of 50 to 70% typically in different reservoirs. The second question is, wherever water goes through, like a rock like this, it's going through these pores, but it's not displacing all the oil, because these pores are so tiny, the capillary pressure holds onto this oil. So everywhere the water goes through, there is a remaining oil saturation or residual oil saturation that's left behind. We call that SORW, O for oil, R for residual, due to water flood. Okay. And this residual oil saturation, or the fraction of the pores that's occupied by oil, is of the order of 30 to 40%. So in well-swept areas, we are still leaving behind 30 to 40% oil. Okay. So you can see the efficiency. So efficiency of this is of the order of 2/3 or a half to 2/3. The efficiency of this is of the order of 50 to 60%. So if you multiply that, then you find the real efficiency. In some reservoirs, the mobility of the oil is very low. Okay? Mobility of the oil is given by the permeability of the rock multiplied by the relative permeability of that oil divided by the viscosity of the oil. So if you have a very viscous oil, this viscosity is very high. That's why this mobility is low. So it doesn't flow fast enough for you to produce. If you have a tight reservoir like a shale, this K permeability is very low. It's only of the order of a microdarcy, so it doesn't flow very well, so you don't produce. So these are the reasons why we are leaving behind. In some sense, for each reservoir, we got to figure out where the oil is left behind. Is it due to this lack of sweep, or is it due to this residual oil saturation in swept areas, or is it due to low mobility? Once you figure that out, then you can come up with a process to enhance this oil recovery. All right, so with that, we come up with 3 methods to how to get this oil out. One is called the chemical method. So this is like using, washing your clothes, using some surfactant or soap, okay? So we use surfactant and polymers to mobilize this oil, reduce these capillary forces, and move them out of the pore space. The second method to clean this sand from the oil is a dry cleaning method. So this is the method you talked about, like using supercritical CO2, do a dry clean and get the oil out. The third method is the thermal method. When you call the steamer guy, he comes and steams your carpet, right? So we inject steam into these especially viscous oil reservoirs, and as the temperature goes up, the oil viscosity comes down, it starts flowing, and you can flow that oil out, right? So now I'll talk about these methods in a little more detail. So here is the chemical EOR method. So in this process, we use soap or surfactants, we use polymers, and sometimes you add some alkali, like sodium hydroxide or sodium carbonate to it. So what each of these things do is Surfactant reduces this interfacial tension between oil and water. So it makes that interface very flexible, so it can squeeze through the tight pores. Polymer adds viscosity to your water. So if you add some viscosity to water, it doesn't flow very fast. It makes a very nice displacement of the oil instead of fingering through the oil. This alkali, like sodium carbonate or something like that, would increase the pH, reduce the adsorption of these chemicals, surfactant and polymers on the solid. And that's how it helps in improving the oil recovery. So typically what you'll do in your injection well over here, you will inject some surfactant polymer first, about 0.3 pore volumes, a concentration of 1% or less, and then follow that with just some polymers for another half a pore volume to a pore volume, and then just go back to your water. And that displaces most of this residual oil and takes them out. In some reservoirs, so that's what you would do if you are leaving behind a lot of this SORW, meaning a lot of oil has been left behind, even in the swept area. This is the process to use. Sometimes the oil left behind is not that much, but the sweep efficiency is not very good. In that case, all you need to do is increase the polymer concentration, just inject some polymers. Okay, that's if you inject some polymers with water, and this amount of polymer you inject is typically 0.1 weight percent to 0.5 weight percent, so very little, not very expensive. And your viscosity of the water will go up, your sweep efficiency will improve, and you'll get a lot of oil into these wells. All right, so these are some of the chemical EOR techniques. Again, I'm going to come back in a few minutes and talk more about these polymers. The second method is this gas EOR method. This is where you inject the CO2, like in the last discussion you guys discussed. Or you can also inject hydrocarbon gas. If you inject CO2 at high enough pressure, it can mix with the oil, reduce that interfacial tension, and mobilize that oil. And sometimes this process is done in a WAG form, that is, you just don't inject continuous gas. You inject a little bit of water, then alternate with a little bit of gas, and so on, to slow down the gas. Another way of slowing down gas is foam. So you inject a little bit of surfactant water, then you inject gas, then surfactant water, then gas. If you do that, you form foam inside the reservoir, and that makes a nice stable front for oil to be dispersed very effectively. And the third method is this thermal method, where you inject steam. Nowadays, they are doing this something called SAGD, steam assisted gravity drainage. What they do is they have one horizontal well over here where they inject the hot steam. When hot steam comes out, it generally goes up and heats the oil over here, and oil gets to be less viscous, and it drains. It's light, it's heavier than the steam, so it falls down, so comes down, and they produce that in this producing horizontal well. So you need a well pair to this SAGD. And you put lots of these wells and you drain this area out. So if there isn't much horizontal barriers in this layer, this is a good technique. Otherwise, you can also put vertical wells and do steam injection from well to well also. This heating, you can do by steam. Sometimes you can do a combustion, meaning you try to inject a little bit of oxygen and light a fire over there. If you light a fire, the temperature goes up. It makes the water steam. It also burns the oil, and the oil temperature goes up. Oil becomes lighter and flowable, and it flows to the producing wells. The third way of heating is put some electromagnetic waves. So if you can put some microwave radar type of things and inject some electromagnetic waves, you can heat the water surrounding the well, and that water heats up the oil, and the oil becomes lighter and it can also flow. So there are different techniques of thermal EOR also. So I want to give you a perspective on how advanced these techniques are. So what I have here is some kind of time scale or more different processes, and this is the process maturity. So basically these processes are pretty mature, are being applied in the field. These are being demonstrated in pilots, they're coming. These are still in R&D stage. So you can see here the steam processes, polymer flooding, miscible gas like CO2 flooding, these are being applied. The SAGD, that is using steam in horizontal wells, is also coming on. There are some water flooding processes with changing the composition of the water. This is the chemical flooding, alkaline, surfactant, polymer techniques. High pressure steam injections, in situ combustions. Here there are some novel techniques like catalytic upgrading of the oil in situ, foams, and using nanoparticles to get good properties for these displacements also. Okay. So let's now get a little bit deeper into polymer flooding. As I said, in polymer flooding, it's a very simple process. All you do is inject polymer with water. That's all you have to do. And what it does, it viscosifies the water. So if you have a little bit viscous oil and you inject water in this well, and you have some production wells over here, water will finger through. It won't make a nice displacement. But if you viscosify the water with a little bit of polymer, you'll make a very nice displacement, efficient displacement. So you get a lot of oil out this way. This is what looks from the top view. On the side view, you may have different layers of different permeability in your rock. Okay. And if you have a high permeability zone, that's where the water will pass through, not displace much in the other zones. But if you use a polymer, there is something called cross flow, and that can improve that front a lot better, have a nice displacement efficiency. And so this is what, as regulators, I guess you have to watch out for. What chemical are we putting in this process? So typically what people use is something called a hydrolyzed polyacrylamide. It's a pretty cheap polymer, about $1 per pound. It's called HPAM. It has a typical molecular weight of 5 to 20 million. As you go to longer polymers, it viscosifies more for the same mass of polymer. It typically comes in powder forms or emulsion forms. It's low cost. We add typically of the order of 0.1 to 0.3 weight percent. So we are not adding much. But in oil fields, anything you do, I mean, this 0.1 weight percent can add up to a lot, okay, because the volumes are big. So right now they are doing a flood like this in Alaska, and they worry about the logistics of how to take this polymer from lower 48 to the north slope of Alaska. So they use planes, ships, trains, and trucks at the end to get it there. This is a second kind of polymer people have used. This is called xanthan gum. This is a biopolymer. This is the other polymer is very flexible. In some sense, it has some good properties. This is more of a rod type of polymer. Okay. Typical molecular weight again is 2 to 15 million. This usually comes in a froth, sometimes as a powder. This is sensitive to biodegradation. So they will add a biocide along with it so that the bugs inside the reservoir don't chew it off. Good thing about this is you don't have to use a lot. The concentration typically used is like 0.01 to 0.1 weight percent. Use less of it, but this is more expensive than the other polymer. But this polymer is very safe. In fact, it's probably used in ice creams. Here is a laboratory plot, polymer flood. So here, if you take a core and it's filled with oil, and if you do a water flood, your oil saturation comes down like this. As you can see, we started at 90%. It comes down to about 50% over time. But if you use the polymer in less than 1 per volume, the oil saturation comes down to 25%. Okay, so that you can see this is the extra oil you get out if you use a viscous fluid with this polymer. And this has been demonstrated in fields. I just show in many fields. I just show one example. This is from Canada, Pelican Lake. So in some parts of the reservoir, they had done primary recovery, then they did water flood, then they did after water flood, they did polymer flood. They got a recovery like this. And this one, if they don't do water flood, straight go to polymer flood, also they get pretty high recovery. So using the polymer, they can maintain this high rate. So it's very effective for viscous oils. Here is sort of some summary from that polymer flood in Canada. I guess I've talked about that. So let me talk a little bit of the price. So you have to put in some horizontal wells over there, and this was the cost. Some polymer water facilities, that's the cost. Polymer cost itself for a barrel of oil was only like $4 per barrel. And other maintenance costs. The total cost was of the order of $14, but the incremental cost because of this chemical was only like $4 per extra barrel of oil recovery. So it's a fairly cheap process, the polymer flood, but it's of course applicable to a certain kind of reservoirs. So here are a few other floods that lately has happened. I talked about Pelican Lake. In India, Kern Energy is doing a polymer flood. It's going very well, and these are some papers about it. In offshore Angola, there has been a polymer flood to demonstrate what to do in offshore situation. Total Energy did that. Chevron has done an offshore oil well offshore Britain, about 100 centipoise type of oil. That also has worked out very well. Hilcorp is doing this polymer flood in Alaska, started about 2-3 years back, and they're seeing very good results. So with that, I'll stop with the polymer flood and get into a little bit of the Huff-n-Puff in EOR shales. Right. So this is a map of shales in US and Canada, including Alaska. So as you know, there are a lot of shales around, and there are some fields people have identified. I guess the orange ones are gas fields, and these ones, the blue ones, are more oil fields. Right? And you can see the impact of producing these shales for oil. If you look at the total US monthly crude oil production, it was going up to 1974 or so, then it started coming down, but we turned it around in around 2007 or so, and it has been going up since then because of the shale oil productions. And this is a projection of what the shale oil production will be. These are different projections at different years, as you can see over here. And as you go from red to yellow, it's been going up as as time passes on, people feel more confident about producing these oils. And in fact, this is the latest one. This is the production from the oil. As you can see, for until about 2050, there will be a healthy amount of shale oil production in future. And these are different fields. These are estimates for different fields. But yes, we know about 60% of US oil production is coming from shales. But in each well, if you look at it, the production is declining very fast. Okay. About 75% drop in production in 1 year. Okay. So in about 2-3 years, now the production goes down to very low levels. Okay. And in fact, the oil recovery in these few years is only less than 10%. It's more like 5 to 8% in these wells. So to keep up this production, people just go drill new wells and frack more. But can we do something to get more oil out of these wells that we have already drilled? Okay, that'll be more efficient. Okay. So that's what this Huff-n-Puff process will address. So let's ask the question, why the recovery is low after this primary recovery. Okay. Basically, we drill wells, we fracture, and then we depressurize. Okay, that's how we are getting this 5 to 10% oil out. So these are several reasons we can list. One is extremely low permeability of these rocks, like microdarcies. There's limited reservoir energy. Okay, so this energy is trying to push this oil through these very low permeability rocks, but only to some extent. Then as we depressurize, we have several micro fractures in the shales, they close. Okay. Then also as the oil is coming out, some solid material from the oil might be dropping out and blocking pores, organic depositions. Sometimes some of the frac water might be accumulating at these fracture faces and blocking the oil flow. So the question is, can we do something about these things and improve the recovery? So here are some of the techniques people are trying out. One mechanical technique is go do refracking. So go back into those wells and try to put more fractures. And that's not that easy because you have to figure out how the stress fields have changed once you have done some fracturing and where exactly can you refrac. That will give you new fractures. The other techniques that I look at a little more is these chemical techniques. This gas Huff-n-Puff, taking CO2, injecting, pressurizing, then depressurizing. You can do a similar sort of things also with some kind of water solution, some kind of surfactant, some other chemical water blends. You can also do something to put some propants inside the microfractures. So you have to do some micropropants or some other technique to keep these microfractures open. Then also you can improve the recovery. We have also looked in a little bit into in situ heating, but we haven't done a whole lot about it. So anyway, today we'll talk about this gas Huff-n-Puff. So this is the Huff-n-Puff technique. Okay. So where we will inject some CO2. Okay. This is a slide from conventional reservoirs, so it shows vertical wells, but this can be done in a horizontal well also, same sort of way. So we'll inject some CO2 and let it soak for some time. Okay, a soak stays, days to weeks, and then we'll produce back. Okay, so what we need to do in order to do this, we need a gas compressor. Okay? So where we want to raise the pressure to the order of 5,000 psi. So initial reservoir pressure in these reservoirs are typical, they're pretty deep. The typical pressures are of the order of 7,000 psi. So there are no problems with extra fractures or anything at 5,000 psi, but this can provide that energy to the oil and can produce some more oil. So as a regulator, I guess you have to worry about to what pressures are they raising this thing to. Are they going to compromise any part of the well or anything? So is there any gas leaks or anything to well integrity? This can be done not just with CO2, but with also hydrocarbon gases. But if you use CO2, you got to worry about corrosion of the wells and some integrity issues due to that. So in the laboratory, this process works very well. This is from a paper. You can look up some details over there. This shows some time of hours that they injected and soaked, and then they produced back. You can see most, like if you use ethane, that's green, CO2 is red. You got pretty high oil recovery in little bitty lab cores for most gases, except for nitrogen. If it's really a dry gas like nitrogen, doesn't do very much. But any other gases like this do pretty well. For methane, and if you have lots of methane, you have to go to little high pressure to achieve the same kind of result. With ethane and CO2, a little bit lower pressure will give you that. This is some field result reported by EOG, and this is from a JPT article. This shows that the primary recovery was going like this. At that point, they started this Huff-n-Puff, and their response is estimated to increase the recovery by 30 to 70%. So there have been quite a few tests in the Eagle Ford and in Bakken, but not much details are published. So the companies can consider it a little confidential, so they don't give you all the details, but there have been quite a few tests. So what's coming is, in addition to CO2 Huff-n-Puff, you can do something with some chemical blends. You can take your brine, KCl brine, and add some surfactant that changes the wettability and removes the water blocks. You can add some persulfate type of salts that can react with kerogen and take it out and improve the permeability. And you can add these in addition to CO2, and that could also help the CO2 Huff-n-Puff process. So I'll sort of try to conclude over here. My time is up. So EOR doesn't have to be the end of the road. A lot of people consider it that way, but it doesn't have to be. You can apply EOR techniques even before you apply the primary recovery techniques. Okay. Or you do a little bit of primary, do just a little bit of secondary, then go into EOR. You can apply it early. Earlier you apply, better results you get. There are many EOR techniques, and some new ones are getting field tested. Polymer flooding improves sweep efficiency. It's ideal for viscous oil reservoirs, and it's fairly cheap. So it's getting applied in this low price oil environment. It's getting applied. As I said, in Alaska, there is a field in Milne Point, Shredder, called Shredder, where there is like of the order of 10 billion barrels of oil. So they are starting now to develop that with this polymer flooding. Shale oil reservoirs produced mostly by depressurization, but the amount they produce is only 5 to 10%. This gas Huff-n-Puff can improve oil recovery, about 30 to 70% additional of what you have produced. And CO2 and these hydrocarbon gases can improve oil recovery by developing miscibility and adding reservoir energy in these shale reservoirs. With that, I will stop and take any questions you may have.
Thank you, Kishore. I'm going to pass it over to Margaret to handle the questions at this point before we go to break.
Kishore, thanks for this amazing talk. And I have to say I knew about quite a few of these techniques, but definitely not all of them. But maybe while we're waiting on maybe some questions from the group, could you just talk about what does like a reservoir engineer do to figure out which one of these techniques to use? I mean, is it
Right.
that it go through a checkoff process or?
That may be my next slide. Let me see. Okay, let me get out of my slide mode. How do I click to exit? Yeah, so yeah, there it is. Okay. So this is the slide I didn't show. So there we do have some screening criteria. That's where you start. Okay. So for and you can get that publication. So depending on what the oil is, you figure out what is the most suitable technique, and you start with this screening table, then go do deeper digging into it and figure out what's the right technique.
Okay. Was the Huff-n-Puff, since you're essentially trying to re-energize the reservoir or adding some new energy, and you're also adding gas, will that puff phase, will that be somewhat equivalent to flush production?
Yeah, right.
I'm just interested about equipment and processes and things like that.
So the puff stage won't be all that different, but it's the, the huff stage, you're going to pressurize, right, with these gases. So you want to make sure you never injected anything, you only produced. So all your cements and other things are good, nothing's leaking out. And you are going to about 5,000 PSI pressure. Whereas when you are producing, it's typically at 1,000 PSI bottom hole pressure or something like that. So you're going to higher pressure. So those are the things you should check for. Yeah.
Okay. We have a question from the participants. Logan is asking, are there any scenarios to where nitrogen would work better, or why does nitrogen not work as well as CO2?
So first of all, nitrogen takes very, very high pressure to be miscible. So it's not developing miscibility in 5,000 PSI pressure. Okay? And these are pretty high temperature reservoirs. So you need a little bit higher pressure to develop miscibility. So that's one. And also nitrogen's basically bottom line, it's not that soluble in the oil. What you want is a gas that solubilizes in the oil, right? If it solubilizes in the oil, it gets into the oil phase, it's in the liquid phase now. And then when you load the pressure, it's going to nucleate and make a bubble inside that liquid, okay? When you make that bubble inside the liquid, it's going to push some liquid out before the bubble can get out. And since nitrogen doesn't get into the oil, doesn't make many bubbles, so it doesn't produce much oil. So methane, ethane, CO2, these are all good gases, but nitrogen isn't.
Okay. Another question from R. Greg. Aren't CO2 expensive? Isn't CO2 expensive on the front end due to corrosion issues with carbon steel equipment?
Right. No, that's the corrosion is definitely important. So if CO2 sequestration, there are some incentives for CO2 sequestration that can help the CO2 process in some sense, right? But corrosion is definitely an issue. If you work with hydrocarbon gases, that's not a problem. So most of the operators in Texas are actually doing hydrocarbon gases. Especially in West Texas, there is a bubble of C2, right? Hydrocarbon gases. So they want to inject something, use that to get more oil out.
I know that the pilot that's being planned by Oxy in Colorado is going to use gas from a gas processing plant.
Yeah, yeah. So that helps with the corrosion. Right?
Another question, John. I'm going to just read these off instead of asking people to, do all the unmute, mute. It seems kind of complicated. Hopefully that's not going to bother anybody, but on the Huff-n-Puff EOR, are you looking for a certain pressure or volume of CO2 to be injected?
We're looking for a certain pressure. First of all, we want to exceed the minimum. There is something called a minimum miscibility pressure. where the gas and oil almost become miscible. Okay. We want to exceed, and that pressure with some of the oils we have worked with more like 2,500 psi or something like that. Okay. So we want to exceed that, and we want to go beyond that just to provide more reservoir energy also. So in something in the range of 3,000 to 5,000 psi, I think is what we're looking for. And one thing we found out, if you want to get the pressure in the gas to 5,000 psi, you need a big compressor, right? Another scheme we have sort of looked into is how about you inject the CO2 to up to, let's say, 2,000 psi. Then you inject this water or water plus some of these chemicals that may benefit you, and let that water pressurize the gas inside the reservoir to 5,000 psi. Okay, then you may be able to avoid big compressors and also get the benefit from these chemicals in the water.
Okay, I think we're at the end of our time right now. We've had a great discussion. There are a few more questions coming in, so hopefully we can handle those in the panel discussion later today.
Sounds good.
Hillary?